So in the absence of any question, then we can start looking at geologic time. Now, when we talk about geologic time, we want to learn about dating, all right? Dating. And dating, we want to give ages or dates to the ages of rock. And there are two principal means we can use to achieve this. One is called the absolute dating, and the other is called relative dating. Absolute dating, it means that we are establishing precisely how many years ago a given event took place, like 1,000 years. It's like when I ask you, how old are you? Okay, so you say I'm 19, I'm 18, I'm 17, I'm 20, 24. That is absolute dating. Relative dating is like you saying, okay, I'm older than Kofi, or I'm older than Amma. You've not given a specific age, but then you are trying to place historical events in their correct order, right? You are placing historical events in their correct order, but you are not producing a numerical estimate or value of how many years ago the events happened. That is relative dating. But absolute dating, you are stating precisely how many years ago the given event took place. And the main means by which we achieve absolute dating is through radioactive dating. All right, radioactive dating. Now, the problem is that only some types of rocks and fossils can be numerically dated. So all other evidence of ancient life must be found or related to age-dated materials. That is materials that we have already dated using the principles of relative dating. All right, so now we are going to learn the principles of relative dating. And this is connected to a branch of geology known as stratigraphy. What is stratigraphy? It's a science of rock strata or layers, all right? It's a science of rock strata or layers. That's a stratigraphy. That's a sub-discipline of geology. All right. So we know sedimentary rocks occur in layers, right? So, and these various layers accumulate over time. And the principles of stratigraphy are very easy, all right? They are very simple, but it's not very easy when we try to apply them to real rocks. So in this session, we are going to attempt to look at the principles one by one, and you have to pay rapt attention as we try to learn the principles, all right? So we have to know the principles and should be able to support the principles with drawings or diagrams. So let's begin to learn the principles one by one. The first principle is the principle of original horizontality. And the principle states that rock sediments are laid down in horizontal succession, forming horizontal or nearly horizontal beds. What does that mean? Let's look at the rock here. When we talk about a sediment, it's nothing but a particle, rock particle, a particle formed from weathering of a rock. All right, so a sediment is nothing but a rock particle, a piece of a rock particle, like soil, sand, that's sediment, all right? Here, look at the rocks here. They are inclined, the beds, that is the layers of the sedimentary rock are inclined, right? What this tells us is that the rock did not form this way. Originally, it was horizontal, all right? This rock was formed horizontally, but now we are seeing the rock this way. The layers are now like this, all right? So since we are now seeing it this way, it tells us that this was how this rock, all right, was formed like this at first. And then due to a geologic event, it became like this. So the rock sediments are laid down in horizontal succession, forming horizontal or nearly horizontal layers. It means that non-horizontal layers were tilted or folded. So this was tilted by some geologic events after they were originally deposited. So that's the principle of original horizontality. All right. The next principle we want to now look at is the principle of lateral continuity. Lateral continuity. So original horizontality is talking about the angle, the fact that they were always horizontal, right? Now, lateral continuity talks about the distance. All right. So lateral continuity, the principle of lateral continuity states that rock layers extend for some distance over Earth's surface. So from a few meters to hundreds of kilometers. All right. So it means that we know they are horizontal like this, but then they are also continuous. So from town to town, city to city over long periods. So this is what lateral continuity. All right, very continuous. So it means that if we find that the continuity is broken, then it is because we have some folding or faults causing the continuity to be broken. All right. So if we have the continuity to be broken, then it's because we have some fold or some faults that broke the continuity. Is that clear? So a fold or a fault might have broken the continuity, and that's why we no longer see it that way. I hope that is clear. All right. So now we know the difference between lateral continuity and then the principle of original horizontality. So the principle of lateral continuity states that rock layers extend for some distance over Earth's surface, from a few meters to hundreds of kilometers, depending on the conditions of deposition. So we should expect over a long distance of deposition. All right. So if faults in severe folding and erosion may have separated the originally continuous beds into what is now looking as if they are separate. All right. The next principle we want to look at is the principle of superposition. So watch carefully. This is layer A. This is layer B. And then this is layer C. So I have layer A. All right. Then after that, I have layer B here. And then I have layer C. All right. So these are all layers. So this is what's A. This is what's B. And this is C. Right. So this principle is basically saying that A is older than B and B is older than C. A is the oldest. Why? Because the principle of superposition states that sediments are laid down in horizontal succession, forming horizontal or nearly horizontal layers. All right. So first, we have the horizontal ones. So if this is number 1, and this is what 2, and this is what 3, right? Then it means 1 must be older than 2, 2 must be older than 3. That's clear. That's the whole principle of superposition. So it states that sedimentary layers are laid down in horizontal succession, forming horizontal or nearly horizontal layers. And unless the entire sequence has been overturned by maybe a fault or disrupted by a faulting, the layers at the bottom are older than those at the top. So that's clear. The layers at the bottom are older than those at the top. So that is the whole principle of superposition. We hope that is clear. Then the next principle is the principle of cross-cutting relations. Cross-cutting. So cross-cutting, this is what we are talking about basically. It states that rocks or other geologic structures or features like erosion or intrusion that cut across pre-existing rocks must be younger than the rocks that they cut across. So let's see. I have here these rock units. All right. So I have these rock units. All right. These rock units. All right. So in here, it means that this is 1. Is that not it? And here we'll have what? 2. So from the principle of superposition, we know that rock number 1 is older than rock number 2. Is that not it? All right. Now I have first. Right. So now I have this like a dike cutting across. All right. So from the principle of cross-cutting, it says that rocks or other geologic features that cut across pre-existing rocks are younger than the rocks that they cut across. So it means that this number 3, all right, should be the youngest. The oldest would be 1 and 2 from the principle of superposition. And because this feature or structure or rock, all right, this intrusion, this is an intrusion, a cut across the original rock, it must be the youngest one. In here, watch carefully. All the white you are seeing, this one, this one, this one. There were intrusions. The original rock is this one, right? The black one. That's the original one. So it means that all these intrusions must be younger than the original rock. That's the principle of cross-cutting. It states that rock or other geologic features, erosion or intrusion, all right, that cut across pre-existing rocks are younger than the rocks that they cut across. All right. In other words, the rock is older than anything that's any geologic feature or structure that cuts it. So that's the principle of cross-cutting. I hope that is clear. All right. So here, if we have a fault, then it means that the fault must be younger than the original structure. So then now we can move to the principle of faunal or fossil succession. Faunal succession. So what does this principle say? So according to the principle of fossil or faunal succession, it states that fossils change in vertical succession. And for this reason, the fossils that are in the lower layers must be older than those that are in the upper layers. All right. Fossils change in vertical succession. Fossils in lower layers are older than those in the upper layers, overlying layers. So in here we have A, B, C, D. These are different rock layers. By now, I'm sure we know that rock A is older than rock B, and then B older than C, C older than D, and then E. Is that not it? All right. Now, what we are basically saying is that if we had a dinosaur bone, all right, let's say we take the first layer, then I had a bone of a dinosaur, all right. Thereafter, I have this second layer coming, and then I have the bone of a different animal. Then after, again, we have another layer. Then we have the bone of a different organism. Now we know from the principle of original horizontality that, okay, that was formed or horizontal beds first. We know from the principle of superposition that this layer 1 is older than this one, and the youngest one is this one, unless the beds have been overturned, unless they've been overturned. All right. If they've been overturned, what does it mean? If they've been overturned, it means that we are now going to have this followed by what? This. And then finally, this. All right. It means we had this followed by this and then this coming. So then we know there has been an overturning. All right. There has been an overturning. All right. And we can match that if we know how most of them were originally formed, we can determine whether or not they overturned. All right. But for now, we are concerned with the normal layering. So the dinosaurs should have lived and died before the conodonts or maybe the graptolites. Is that not it? This means that when I see this, I'm able to tell that this is the oldest, followed by this and this. All right. So that it implies, therefore, that the principle, more or less, is saying that fossils change in vertical succession. So this is a vertical succession. Fossils change in vertical succession, and fossils in lower layers are older than those in the overlying layers. And furthermore, the same vertical change in fossils occurred in different places. So we have dinosaur, conodont, graptolite, just as an example. All right. Now, it means that if I go to Nigeria, I should find the same layers. But maybe when I went to Nigeria, I only found this one. Maybe when I got to Nigeria, somewhere far away, I found this layer with so I found this layer. Then all the ones on top are missing. I have a different rock altogether. All right, and now I have this fossil. So based on this principle, it means I should be able to correlate. I should be able to correlate the one from Ghana with the one in Nigeria, right? So here, the dinosaur bone is here, the same dinosaur bone is here. It means that this rock and this rock have about the same ages. Is that not it? You get the picture. It means this rock and this rock should have about the same age. All right. But then I don't have the conodont. It's missing. The graptolite is also missing. All right. But then maybe I now have this particular layer, a new rock layer. Let's call it maybe a sandstone or something. So it means, what this means is that erosion might have removed these two layers here in Nigeria. All right. So it means that this rock should be far, far older than this one because two layers are missing. So this is how we can apply the principles of superposition and the principles of faunal succession. All right. All right. I hope that is clear. So based on faunal succession, we can correlate from one location to another location because the principle states that fossils change in vertical succession. So fossils in lower layers are older than those in overlying layers. And furthermore, the same vertical changes in fossils occurred in different places. So this is the practical implication. The one we just stated was cross-cutting before this principle, and then we see any structure that cuts across must be younger than the layers it cuts across. Is that clear? All right. So once that is okay, then we can move on to the next principle. So as far as the next principle is concerned, all right, As far as the next principle is concerned, Juliet, I think if you cannot hear it, maybe due to your network. All right. You should just check carefully. You should adjust your volumes or look at your network. All right. Yeah. All right. Do you all follow all that we have done so far? Is there any question? Is there any question on all the principles we have looked at so far? All right, Gilbert. So I'm going to take this last principle again. All right. It's the principle of faunal or fossil succession. The principle of fossil or faunal succession. Yes, Kalenam. So I'm going over the last, the fifth principle again. The fourth principle has to do with cross-cutting. And let's follow this diagram here. We have 1, 2, and 3. I'll show you, and just hold on. I have a real much clearer pictures on that principle. You'll soon see that. All right, it's in your slides. But then it means that when you have a rock and any structure cuts across it, all right. So we are saying that if I have a rock like this, all right, then I have another structure cutting across it. I have this structure cutting across it. The yellow structure is younger. Is that okay? The yellow structure is younger because it's cut it. So Clenam, basically what we are trying to say is that if you are not in a relationship, you cannot get your heart broken, correct? If you are not in a relationship, you cannot get your heart broken. Is that not it? So it means that for this to be able to cut across this particular rocks, it means they should have been there before it came. That's the meaning of the cross-cutting. All right, that's the meaning of the cross-cutting. All right. Then as far as the next one is concerned, which is the principle of faunal succession, I have rocks here, 1, 2, 3, 4. All right. Then I have the dinosaur bone here, a different animal bone here, a different animal bone here, a different animal bone here. From the principle of superposition, we know that the rock 1 must be older than 2, and then 3, and then finally the fourth one is the youngest one, right? The same way means that the dinosaur bone here must be older than the bone here, and it must be older than the bone here, and also the bone here. Most animals only spend a few million years before the entire species disappears, right? All right, so as far as the principle of faunal succession or fossil succession is concerned, it states that fossils change in vertical succession, and for that reason, fossils in lower layers are older than those in overlying layers. And furthermore, the same vertical change in fossils occurred in different places. All right. So what we are saying is that if we have rock 1, rock 2, rock 3, and rock 4, with dinosaur bone 1, here we have the bone of maybe another animal, say a conodont. Here we have graptolites. Here we have a different animal remains. We know that this rock is the oldest, right? It means the animal whose bone is here must be older than this one because it should have died and was buried inside this sand that's cemented long before this animal lived. All right. So it means this should be the oldest organism, followed by this and this and this. The same way, this should be the oldest rock, followed by this and this and this. We are saying the same vertical change occurs from place to place. If I travel to Nigeria and I find the same type of rock with the same dinosaur bone, it means that this rock and this rock must have the same relative age. The age must be close. If this is about 2 million years, this should be around the same age. But if in Nigeria, I'm supposed to find the same thing, right? But if I don't find the red and the green, but I find the yellow and the black, it means the red and the green were removed by erosion before the black formed on top of the yellow. Is that clear? Because definitely, because the same structure should have formed in Nigeria because of even lateral continuity, we know that there are some layers missing here. So we can correlate the age here to the age here and correlate, no, some of them there are missing. All right. So the age of this black one must be the same as the age of this black one. That's the principle of phonal succession. All right. So I hope that is quite clear now. So now we can make progress. The next principle we want to look at is the principle of inclusion. Inclusion. Now, there are two words we need to remember. We have intrusion and we have inclusion. All right, intrusion and inclusion. Intrusion is the one we talked about, where the dike or the structure cuts across the other one. Yes, so Olivia, the main difference between the two is the presence of fossils in the rock or phonal succession. That's correct. All right. So we want to look at this two, intrusion and inclusion. Intrusion, it means that we have a volcanic eruption or, yeah, and then it's cooled down through the rock, right? So we have intrusion. Inclusion, watch here carefully. I'm going to try to explain this one. All right. All right. So I have this yellow rock. Then somewhere in there, I have this black one. It's very small. It's not very big. This here, all right, this one. So the black one is an inclusion, all right? All right, so making progress with that. All right, making progress with that. So I was trying to talk about inclusion. Inclusion. All right, inclusion. So we have this yellow rock. In the middle, we have a small black. Small black. This one here is an inclusion. All right, this is an inclusion. So that's clear. Inclusion. It was not part of the rock, it just found its way there and it became part of the rock. It's an inclusion. So the principle of inclusion states that any part of an existing rock that is incorporated into another rock must be older than the rock in which it has been incorporated. Watch this layer here. Are you all seeing this rock here? This one. It's totally different. And it is completely surrounded by this other rock, right? It's not as if we just took it from somewhere and put it there. It is just an existing rock, a pre-existing rock that became trapped inside this rock. Do you understand that? So it must be older because it was existing before we had this, the new one formed. All right. So then this inclusion must be older than the surrounding rock in which it has been incorporated, the rock in which we find it. That's the meaning of the principle of inclusion. But when we talk about intrusion, we are talking about something like this. This is an intrusion. All right, like a magma cutting across, that's an intrusion. But this is an inclusion. Is that clear? How does this form? For it to form this kind of inclusion, it means the rock was there and then maybe a river kind of carried it and then it's deposited it into a sand bed and then later on it's cemented, everything cemented together and it's formed a sedimentary rock. Or the other way is what I'm going to show you right now. I have this blue rock, right? Then we have magma cutting across this, right? So here we have cutting across. It's going to melt some of the blue, but then the magma finally also form its kind of rock around here. All right. But when it moved through the blue layer, it might have carried some pieces of the blue. So now we have this. This is an inclusion. The blue here is an inclusion. All right, it is an inclusion. So this inclusion, if it is in an igneous rock, we call it a xenolith. Xenolith. Xenolith means foreign rock. Xenolith means foreign rock. So this right here is a xenolith. Xenolith meaning foreign rock. It means it was not originally part of this rock. It just became trapped inside the rock. All right. Great. So once that is clear, then we can move on. So now we know what a xenolith is, right? This is a xenolith. It's a xenolith. The general term is inclusion. If you're in a sedimentary rock, we are going to call that an inclusion. All right. So we now know that that is different from an intrusion. So here we have examples of xenolith, right? We have examples of xenolith. All right. So these are various xenolith. All right. So we see that this is an intrusion, and we have this xenolith all around the intrusion. All right. So this is a xenolith. This is a xenolith of this rock is the original one. So we call it the host rock or the country rock. All right, the host rock. It was there before the magma came. And so this one is like this one here now. All right, this is a xenolith, or the general term is inclusions. All right, so once that is clear, then we can make progress. We are going to talk now about another principle that is very similar to the cross-cutting, all right, the cross-cutting. So you remember we talked about intrusion, right? And we said the intrusion must be younger than the rock that is intruded. Is that not it? But cross-cutting, we said that whichever geologic structure cut across the pre-existing rock must be younger. The only difference between this one and that one is that the cross-cutting, it can be a fault, it can be a joint, it can be an erosion, anything. But intrusions, precisely, we are talking about magmatic intrusion, like a rock, all right, a rock. So the principle is very similar. If you know the other one, you can state this one easily, all right? So we are saying that we have this rock layer, all right? So we have this rock layer, and then we have an intrusion. So if an igneous intrusion cuts across a layer of sedimentary rocks, the sedimentary rock must be older than the igneous rock which intrudes it. Is that clear? So the intrusion can be a dike if it is vertical. It can be a horizontal intrusion. So that would be what? A seal. It can be a stalk, a laccolith, batholith, depending on the size. Depending on the size. So that's the principle of intrusive relations. All right. I hope that is also clear. The intrusion must be younger than the rock is intrudes, or the sedimentary rock must be older than the igneous rock which intrudes it. All right. So now let's try to address this. Let's see if we can get the ages of A, B, and C. Let's look at diagram one. We have a dike. This is a dike, right? The vertical intrusion. So it's a dike. Is that not it? This is right here. This one is a dike. B is a dike. A is a sedimentary rock. C is an erosion surface, and D is also a sedimentary rock. All right. So let's see if we can apply all the various principles we have learned so far to name or not to name to determine the relative ages. So it's like the chicken and the egg, which came first, right? Let's try and determine the relative ages. In here, we have A, right? We all agree A must be older than B. Is that not it? Because A came, and this is from the principle of intrusion relations or cross-cutting, we know that B is younger than A. What about C? Yes, C must also, which is the erosion surface, must be younger than B because see here, it's eroded B. If it did not erode B, then B would have continued like this. Can you see that? If B had continued like this, then it means that C was there before B came. That is why it's cut it. But B did not cut C, which means that C is younger. And we can see from the top that part of it has been cut off. It has been chopped off. The tip has been chopped off. So C is definitely younger than B. And after C came, we know that from the principle of superposition and all that, D is the youngest. So now we know A is older than B, B is older than C, and then C is older than D. Then let's look at the case of the second diagram. Once again, we have the sedimentary layer we know is the oldest, right? The oldest here. Let's look at B and C. So B and C, which one is older? How can we determine that? We have to look at the one that is cutting the second one. Is that not it? All right. So we are combining the principles of cross-cutting and intrusion, intrusive relations. Is that not it? Now, we can see here that C has cut B. Is that not it? C has cut B. Why is C cutting B? Because here we can see this part. Look at this part. We can see C going through B. So for C to be able to divide B into two, all right, it means that B was there before C came. So if B was there before C came, then B is older than C. So it means that the dike is younger than the sill. This is sill, S-I-L-L, sill. And this is the dike. So the dike is older than or the dike is the youngest here, younger than the sill, because the dike divided the sill into two. And the dike also went through A. So we know that A is the oldest because A must be there before the sill came and finally the dike came. All right. What about C? In here, this is what? A stalk. A stalk. This structure is called a stalk. All right. Don't forget that much earlier, we looked at these various types of dike stocks and all that, right? So you have to go back and take a look at them. In this diagram, we defined, so these are some xenoliths here, right? Then this, we have a laccolith. Then the whole of this big one is a batholith. You can see the batholith, very big, right? Still, it's a horizontal intrusion, and this is a dike. So now we are applying this terminology. So this is a sill and this is a dike. All right. All right. So from here, we know that the sedimentary rock A formed first because it's in layers and the B is an intrusion, right? So the stock, clearly, the stock, of course, it's younger than the sedimentary rock. Then we can see that C has divided, has cut through the stock. So it is the youngest. Is that clear? It's the youngest. So that is how we apply the principles of relative dating. In the real world, let's see if we can apply this practically. All right, so the big question now we want to ask now is that, so now we want to ask in here, we have a structure, we want to ask, all right, that, so the big question we want to ask is, see, in here we have these structures, right? A, B, this is still B, and then there's another structure. I don't know if you can see it. It's here. C. All right, C. Which one is the oldest? So I am waiting for the answer. I'm asking which one is the oldest? All right, so a good number of you are saying A is the oldest. All right, you are saying A is the oldest. And this is B. Yes, please. How can this, where is slippers? No. But they did orientation, right? But they did orientation. So it's absent. Yeah, once they did orientation, then it's absent. As simple as that. Yeah. All right. So let's make some progress. So I had another class clashing now in a lab, so I have to respond to that. So let's see. Let me see if somebody has said B, and then Randy. So I think Randy is saying B. So unmute and tell us why you are saying B is the oldest. Yes, Vincent is also saying B. I want to hear from Asante is also saying B. Yes, Randy. Why is B the oldest?
Sir, please, I meant A. Maybe it was a typo mistake.
Right, Asante. So that's Esla, right? So unmute and tell us. We just want to hear from you. Yes.
Say. So please, you were like the one that cuts the older rock is younger than the the older rock.
All right. So all in here, in this diagram, in this image. So this image, you can see that's my good self there. Is that not it?
Yes, I think. Say.
That's myself. I'm the same person standing in front of the rock, right? I'm standing there.
Mm.
So now, which one is cutting which one here? The A or the B? Is the A cutting B or B is cutting A?
Say B.
B is cutting A.
Yes.
Are you sure? Is that what you can see? But watch.
Say
To the,
A is cutting B.
all right. So here is also B. Don't forget, this side is also B. So A is cutting B, right?
Yes.
So which one should be older now?
The B.
The B should be older.
Yes.
And A is younger. Is that your final answer?
Yes, please.
All right. So that's okay. So now you get it. Now for +1, give me the geologic term for A. What's the name?
Say
Look at the rock. It's cutting, right?
yes, please.
And is it horizontal? The A.
Yes. Okay, horizontal.
No, is the A horizontal or vertical?
Says
It's what?
horizontal.
A is horizontal. Are you sure? Yes, so the entire class. So that's fine. So I wanted to give you 3 marks, but you don't want it.
Then no, I want it.
But you have to give me the geologic name for A.
Okay.
All right. So yes, fast. Somebody's trying to get a mark. So you have your last chance. Yes, Asante, don't worry, you have your chance tomorrow. So let's make progress. But I'll tell you the
The
whole
principle of original horizontal.
horizontality.
Yeah, horizontality.
No, so that's A is a dike, it's a vertical intrusion. So that's a real world. That's how a dike looks like. It cuts vertically. Is that okay?
Yes, please.
All right. Yeah. Right. So I think I have to give the point to who was that? The first person to mention a dike. That's a Ochri. So you have to remind me and remind the reps. We have to give you your points. All right. That's very good. So it's a dike. All right, that's a dike. There's another geologic structure there. Who can identify it? What's the name of that structure and why? Very fast. You can type if you want. I'm referring to the structure C. I think I removed it. So let me name it back. The structure here, this C here, this is the one I'm talking about. There's another structure there. So what's the name of that structure? Right. So somebody is saying that it's a seal, somebody is saying it's a Pluton, inclusion, stock. So the part we are talking about C, the structure here, that is the C. So we are trying to name the structure C. All right. We are trying to name that structure C. So a seal, inclusion, what, and all that. All right. So we've not gotten the answer, but that's fine. All the answers you've provided so far are wrong. A dike. So we all agree A is a dike. Is that not it? A is a dike, right? So A is a dike because it's a vertical intrusion. You can see my good self there, right? So A is a dike. B, it went through B. It cuts through B. All right, it cuts through B. No, the structure C, the one I circled, is not a bedding plane. Of course not. Do you know bedding plane has to be horizontal or at least in bed? All right. No, the structure C, a xenolith will have to be, if you had a piece of this white here, then it has to be a xenolith. You can just Google xenolith, then you find lots of images of xenoliths online. This is not an erosion surface. All right. Structure C is not an erosion surface. Right. So A is a dike. So it's from the principle of intrusion across cutting, we know it is younger than B because B was there, lateral continuity, horizontality, whatever. It was there. And then it came. This eruption came, this dike. This is a basaltic dike. Basaltic dike, mafic. All right. Let's look at B carefully. Let's look at C carefully. Watch. So we are going to learn a term now. All right. Now, C is a break in a rock, is that not it? So in geology, we call breaks in the rocks, we call them fractures. Fracture. Look at this level. Do you see this one? Look at this layer here. Originally, it continued like this, is that not it? Even though it's not too clear, if you watch carefully, it was supposed to continue like this, but now this part has gone down. This part here is now down. Can you see that? This part has gone down. All right. This part has gone down. So therefore, this fracture is a break in the rock, and one part has moved. We call it a fault. It's a fault. Right? That is a fault. Is that clear? This is a fault. It's a geologic fault. All right. So now we've applied the principle practically. So for the person who was asking me in some comments at the back, can you go over the fourth and fifth principle? So this is the fourth principle, all right? This is the cross-cutting or intrusion relations. Is that okay? Practically. All right, practically. All right. So that was my good self in some years ago when I was doing my master's. Let's move on. So we just mentioned the term faults, and the fault is a planar fracture or discontinuity in a volume of rock across which there has been significant displacement along the fractures as a result of earth movement. So the part that moves down is known as, how do you call it? The hanging wall, right? And the part that remains stable is called the footwall. So this is the footwall, and this is what? The hanging wall. Over here, we have this one as the hanging wall, and this one is what? The footwall. Let me explain. Look at the plane carefully. You should always look at the plane, all right? Can you see the plane? It's going like this. So the one that is whatever is on top of the plane, you have to watch it carefully, all right? Whatever is on top of the plane, or it's like lying on the plane, is the hanging wall. All right. So you can see this block is lying on the plane. Is that not it? So it is this one is the hanging wall and this is the footwall. So this is a normal fault because this one has gone down. Initially, they were at the same level like this. You get that? They were at the same level. All right. They were at the same level. All right. So now we see that this is a normal fault and it's due to tension forces, all right, tension pulling apart. If I should compress the two blocks, then this structure will move up. The block will move up. This whole block has moved up. So this is the hanging wall. So this is a reverse fault, reverse fault. Then there are some other examples called a truss fault, which is a special reverse fault. And we have a right strike slip fault, like just sliding past, strike slip. All right. So in a normal fault, yeah, so Godfred, we are going to meet in class tomorrow, so you can all the questions that you have and ask. Is that okay? All right. So in a normal fault, the hanging wall moves down with respect to the footwall. And then in a reverse fault, the hanging wall moves up with respect to the footwall. All right, so that's the difference. So a fault is a planar fracture or discontinuity in a volume of rock across which there has been significant displacements along the fractures as a result of F movements. All right, so that is a fault. Let's learn now how we can apply these concepts of faulting practically. So before we go there, let's look at the principle of cross-cutting relation. It's similar to the intrusive relation and all that. I think we already did something on that. Is that not it? So we are back to cross-cutting, but now we are focused on faulting, all right? A fault is younger than the rock it cuts across. Simple, that's the principle. So where a fault cuts across a sequence of sedimentary rocks, the relative ages of the fault and the sedimentary rock or sequence can be determined because the fault will be younger than the rock it cuts across. All right, a fault is younger than the rock it cuts across. So let's look at this one now. See here, what type of fault is here? What type of fault is this? Yes, so I'm asking the class now, what type of fault are we looking at? You all agree there's a fault here, right? So normal faults, reverse, normal. All right, so normal. So any of you who wants to explain? So I want one of you to explain, possibly to get some mark. One of you can try to request to put up your hand, request to unmute, and then I'll unmute you and then just call you to give me your view, what kind of fault we are looking at. Yes, so let's see. So let me just call as random. Yes, so Godfred, can you tell us? I'm more Godfred. So you said it's a normal fault. We are asking Prince, we want to know what kind of faults we are looking at here. Yes, I'm more Godfred. So unmute and plus why you are saying it's a normal fault. Yes, a little louder. Yeah, we can't hear you, so just speak a little louder. Yes, Samuel Godfred, what kind of faults are we looking at? You said normal, right? Okay, so I don't know whether it's the network, but we can barely hear you, but it's fine. All right. All right, so yes, we are looking at a normal fault. All right, we are looking at a normal fault. That is true. So we basically want to know, yes, Kelvin, so go ahead and tell us why you think it's a normal fault. Yes, we can hear, I can hear you. I'm sure everybody else can. Yes, Kelvin, go ahead.
Hello, sir. It's a normal fault because the hanging wall moves downwards towards the floor. Hello.
Yes, so which part is the hanging wall?
Hello.
Assuming, yes, so Kelvin, assuming, watch carefully, okay? So assuming this part is A,
Okay.
and this part is B, which part will you call the hanging wall? The left side is
B.
A and the right side is B. So which part is the hanging wall?
The B.
Correct. So Kelvin, remind me no matter what. I just wrote down your name, but remind me you have a +1. All right.
Okay.
Right. So we all agree that the B is indeed is the hanging wall. Is that not it? So we have a normal fault here. And you all see that because this was the origin, they were all at this level, and then the fault took this one down, this brick, and we have a fault. Practically, what this means is that if we were mining gold here, can you imagine when we get here and we continue, our gold will vanish, right? So if you don't know that you are dealing with a fault, you lose all this money here. That is a practical implication. Do you get that? So imagine it's once happened to a company, all right? You are mining here, you get here, you continue, the gold will vanish. So you have to find, you continue, the gold will vanish, the company will collapse. You have to come and find the displacements, the offsets. And you need geology for that. If not, all here, you lose all this amount of gold. And the interesting thing is that when we get here, once again, it vanishes. We need to know that we are dealing with another fault. So there's another fault here again. We have to find the offsets and continue mining. When we get here, because this is a double fault, it vanishes. We'll have to come back and continue mining. It's really important because there's a through. All right. It's really, really important to understand. Yeah. It's really, really important. Yeah, Amwa Godfred, I think I will accept that as well. Yes. So we are dealing with a normal fault indeed. All right. So I hope you all now understand the concept of normal and reverse fault. And the fault is definitely younger than the rock that is cut across. Is that not it? All right. So now let's apply these principles this, and then we can wrap up today's session, and we can meet in class tomorrow to continue. All right. So we already look at now we all know what a normal fault is and then a reverse fault is. So in here, it means that these faults, so we know originally this is a footwall, right? A, B, and C. A is the oldest, followed by B and then C, right? Then here A and B and then a C. All right. So we know that the fourth is the youngest. The fourth is the youngest. Now let's see here. A formed, B formed, and C formed. Then fourth thing happened. Later on, we had what? The fourth is the D, and E formed later. Now it means E is the youngest. Watch here. If the fourth had continued like this, it meant that the fourth is the youngest. But I didn't cut E. Because the fourth did not cut E, E is the youngest. All right, E is the youngest. All right. So we know normal faults occur due to tensional forces. All right. And the hanging wall moves down with respect to the footwall. And reverse faults occur in response to compression. And then the hanging wall moves up with respect to the footwall. And thrust faults are special types of reverse fault, low angle. All right. So do we have any questions? Are there any questions? If no, then let's look at the last thing for the day, which is biostratigraphy. So biostratigraphy basically has to do with using organisms. It's like faunal succession. It's like what I said. You remembered I was correlating one rock in Ghana to another in Nigeria. That is biostratigraphy based on the dinosaur bone. Is that not it? So we know that some species or some fossils found in one rock can be correlated to a fossil in another rock in a different country or somewhere. That's the whole concept of biostratigraphy. Because various species only live for a few million years and then they die away completely or they evolve into another species. So we didn't know human beings are not going to be here forever. Either we die off completely or we evolve into another organism, which is not Homo sapien. All right. Great. So organisms that appear quickly, new species, not one animal, the entire species, they appear for a short time and then they die off. And also their bones are easily preserved or their remains are easily preserved. They are very good for biostratigraphy. All right, they are very good for biostratigraphy. So when we correlate, like what I tried doing in the images in the rock from Ghana and then Nigeria, we can tell not just animals alone, even remains of plants like a leaf dried over millions of years. So we are able to tell that, okay, this one must be older than this one, or this one is younger than this one. Do you get that? So that is the whole picture of as far as biostratigraphy is concerned. That's okay. So we know that until radiometry or radioactivity came, there was no independent way to test the accuracy of relative dating. We can only say this is older than this, but is it true? But now, because of radioactivity, we are able to confirm some of these relative ages, whether or not indeed one rock is older than the other, based on radioactivity. All right, based on radioactivity. Great. So now we know that absolute dating, we already discussed it at length. We know it has to do with naming rocks, or how do you call it? Trying to give the actual age of rocks using radiometry. So we already discussed this, I think, far earlier. We don't have to waste time. That's the whole concept of absolute dating. All right. The fact that you apply radiometric principles to date the rock. All right. So we know that every element, these radioactive elements, they have parent isotopes and what? Daughter isotopes. Is that not it? Parent isotopes and daughter isotopes. So based on this, we can calculate the half-life, the time it takes for half of the average time an atom of a radioactive element remains in the parent state. All right. We call that the half-life. Is that not it? The half-life. The time it takes for half the original amount of the element to decay. All right. That is the half-life, is that not it? So I'm sure you have an idea of this. So based on this half-life, we can calculate first, what was the original amount of the elements remaining in the rock? And what is the quantity of the original amounts remaining? That's the first question. What is the quantity of the daughter isotope? So if I know that it takes 1 billion years for the parents to decay to form the daughter, and I know the quantity of the mother or the parent's atom or isotope, and I calculate the quantity of the daughter isotope, then I can, knowing the half-life, I can estimate the age of the rock. We can use carbon-14, but carbon-14, the half-life is only 5,000 years. All right, so, and we know most rocks are in the ages are in millions of years. Is that not it? Millions of years. So because of that, it's better we use like uranium, thorium, and coal. So uranium-235, the parent isotope is uranium-235, and the daughter is lead-207. All right, and the half-life is 700 million years. So based on this, we are able to calculate the actual ages of these rocks using radiometric data. All right, so this is where we stop for today, and when we meet tomorrow, we'll look at we will wrap up on this radiometric dating, and then we continue from there. So as a reading assignment, I expect you to cover paleomagnetism and methods of dates, and then you have to cover unconformities. What this means is that if we should decide to take a short quiz, is going to be on unconformities. So you should have covered unconformities. Tomorrow we'll be looking at unconformities, and then how do you call it? Geologic timescale. We'll be finishing this tomorrow. All right. Then I think next week we'll start with plate tectonics. All right. So unconformities and the geologic timescale. I'm not sure we may start to plate tectonics tomorrow. It's going to depend on the time. Is that clear? So that is all we have for today. In the absence of any other question, yeah, have a nice day and see you tomorrow. So now we want to talk about breaks in the stratigraphic record. So like I was saying, we know that we have a lot of events that shape up our planets. So we have uplifts where the Earth's crust is coming up. We could have subsidence due to various reasons. We could have deformation and even erosion. And all these processes are acting to shape the particular, or to have an influence on deposition of sediments, all right, in various places, and has occurred over the years and continues to occur. So when sediment is not being deposited, or when erosion is removing previously deposited sediments, we are not going to have a continuous record of sedimentation preserved in the rocks. And we call this break in the stratigraphic record a hiatus. So hiatus is nothing but a break in a stratigraphic record. All right, so that's a hiatus. And if we should find evidence of this hiatus, then we call that evidence of a hiatus in the stratigraphic record. We now call this an unconformity. Unconformity. So what is an unconformity? It's a buried erosional or non-depositional surface. And this buried erosional surface separates two rock masses of different ages, indicating that the position was not continuous, indicating that there was a break in the record. So unconformities are a special type of geologic contact. All right. So a boundary between rocks caused by a period of erosion. It means that we had deposition, then we had erosion. Mind you, we are dealing with millions of years. So there was a pause in sediments accumulation. and followed by the deposition of sediments anew. All right, so that's buried erosional surface that separates two rock masses of significantly different ages is what we call an unconformity. Unconformity. All right. We have three major types of unconformities that we are going to be discussing. So we have three common types. We have angular unconformity, we have disconformity, and then non-conformity. There are some other types like paraconformity, blended unconformity, and then buttress unconformity, but the most important ones are these earlier three I mentioned. So angular unconformity. So this is an image here of an angular conformity. Disconformity, all right, and then a non-conformity. So let's attempt to take this one by one and see if we can understand how all this came about and whether there are some real-world images. What's an angular unconformity? It is the contact that separates a younger, gently dipping rock unit from an older one that is underlying units that is tilted or deformed. From the principle of original horizontality, we know that we should first start in this kind of horizontal succession, laterally continuous, and then we can superposition A is older than B, older than C, older than D. Right. And we had this folding, compressive forces caused this particular layer to fold. So we had compression, compressive forces. After that, what do we have? We had erosion. So erosion chopped off the beds, and we formed this particular type of layering. Subsequently, after several millions of years, we had renewed deposition. So this forms this particular type of layering. And this is what we call this erosional contact separating, all right, the younger, gently dipping rock unit. So this is the younger one. On the ones on top, you see they are not steeply inclined. They are almost horizontal. That is why we say they are gently dipping from the older rocks that are tilted or deformed. So these are the older rocks. We see that these are tilted or deformed. So this surface here is the unconformity. And this particular type of unconformity is called angular unconformity. Angular unconformity. All right. Angular unconformity. So this is another way of looking at it. We have ABC. It may not be just folding. Here we have this tilting, uplift tilting, and then the erosion. After the erosion, we have what? This renewed deposition. So this is angular unconformity. Angular unconformity. So we had a lot of erosion up to this level, and then we had renewed deposition. All right. Then we could also talk about disconformities. And these disconformities are usually erosional contacts that are parallel to the bedding planes of the upper and then the lower rock units. All right, so we do know that some disconformities may be very difficult for you to see in the field directly. All right, because unlike the angular unconformity, in the case of the disconformity, you don't easily see that. All right, you don't easily see that. All right, so let's see here. This is a disconformity. So we have this 1, 2, 3, 4. Then erosion removes 3 and 4, right? Then subsequently we have fresh deposition after millions of years, 6 and 7. So then we are going to have this kind of layer. And it may be difficult for you to tell that whether this is a normal deposition or that there's a significant gap between the other. All right. and that is angular or disconformity. All right. And these are often discovered when the fossils in the upper rock and lower rock units are studied, because you realize that the fossils here are far older compared to the fossils here. Then clearly we can easily now tell. But just with your eyes, it may not always be easy to tell that this is a disconformity. All right. Then the last in the series of the major unconformities, we call that a non-conformity. A non-conformity. So it's the contact that separates a younger sedimentary rock unit from an igneous intrusive rock or metamorphic rock. So in the case of angular unconformity, we expect to see the lower bed to be severely inclined, all right? And then we have an erosional contact, and then we have the younger beds that are gently dipping, that are on top of it. In the case of the disconformity, we more or less had the same rock units, sedimentary strata, all right? So bedding planes, and then this is what is separating the two. But non-conformity is also easy to identify because beneath the non-conformity, we have an igneous or metamorphic rock, and on top of it, we have a sedimentary rock. So what is the non-conformity? It is the contact that separates a younger sedimentary rock unit, which is lying on top, all right, from an igneous rock unit or a metamorphic rock unit, which is below. So a non-conformity suggests that we had a long period of uplift. Then subsequently, we are going to have breaking down of the rock units through weathering, then erosion to expose the older, deeper rock. And then we had renewed deposition. All right. So here we see that we have this igneous or metamorphic rock, IM. Then we have J and K. What happens? J and K were eroded away. All right. Then we now have only the IM, then we have renewed deposition. So this contact that is separating this older igneous or metamorphic intrusive from the younger overlying sedimentary strata, this contact is the non-conformity. So here we have an older igneous metamorphic rock, and then this is a sedimentary rock directly lying on that one. So that's a non-conformity. Non-conformity. So non-conformities and angular unconformities are very easy to identify. But when we are dealing with the case of the disconformity, then that may not be easily identifiable unless we compare the fossil records. All right. So like I mentioned earlier, we have other types of unconformities. We have the blended unconformity. All right. And then it's a type of disconformity or non-conformity with no distinct separation plane. So sometimes it could have some soils, or if you like, we call them paleosols, or pebbles derived from the underlying rock. So it's blended. All right, it's blended. So we cannot see a clear separation plane. Then we could also have one known as the buttress unconformity. So here we have the younger bedding deposited against the older strata. All right, that's influencing the bedding structure. So it's influencing the bedding structure, and then we call that the buttress unconformity. All right. Then we could also look at a paraconformity. So from the word parallel and unconformity. So here the strata is very parallel, like in the case of the disconformities. All right. So there's little apparent erosion when we are dealing with this particular case. But the most important unconformities we need to know . But the most important unconformities we need to know are the first three I mentioned, which is the angular unconformity, the disconformity, and then the non-conformity. All right. So that is the concept of unconformities. So I do hope that is clear. All right. So for the rest of the last thing we want to cover before we take a break today is the geologic time scale. Geologic time scale. So earlier on, I was mentioning terminology like Paleozoic, Mesozoic, and all that. So that's all come from the geologic time scale. So geologists and paleontologists usually represents geologic time vertically. And this arrangement is derived from the vertical succession of rock strata in Earth itself, all right? And the vertical time scale mimics the stratigraphic arrangement. In other words, think about the principle of superposition, all right? So in that case, we find out that the youngest units are below, the youngest units are above, and then the older units are below, right? So think it's just a similar principle. And then when we do that, we are getting this column called a geologic column. And it is breaking, all right, the rock units, the time, the geologic time into units of known relative age. So we are using relative dating to build this particular system, all right? Note that this column was established and fairly well known before geologists had a means of determining absolute ages from radiometry. So we are trying to say, okay, these rocks here are older than these ones, and these ones are older than these ones, and that one is older than that one. So we are building this into a vertical, more or less stratigraphic column, all right? And this is what we call a geologic column. And it breaks the geologic time into units of known relative age. So with respect to that, geologists have divided the Earth history into units displayed in this particular column called the geologic time scale. The units are called aeons, eras, periods, and epochs. Aeons, eras, periods, and epochs. All right. And these are identified primarily by the types of life that existed at these various times. So the two earliest aeons, we call that the Hadean and the Archean. So you see we have aeon, era, period, and epoch. So we remember that the Earth is 4.6 billion years old, right? So this is the beginning. At that time, origin of the Earth, no animals existed, right? This is the approximate age of the oldest rocks. And then after that, we have this particular aeons called the Hadean and then the Archean. These two alone cover 2.5 billion years. So we are left with just about 2 billion years, right? Then along the Archean, when we got to around the Archean, we had the first unicellular organisms. All right, unicellular organisms. And then by the time we got to this particular aeon called the Proterozoic, we had the first multicellular organism. So as far as the aeons are concerned, we have the Hadean, Archean, Proterozoic, and Phanerozoic. You think human beings, we are the last to come, right? We are the very last to come. And we came in the what? The Holocene epoch of the Quaternary period in the Cenozoic era of the Phanerozoic aeon. All right. So humans, we came very late. And then I think this also the geologic records align with the religious views, right? Saying that all the plants and animals came and human being was the last, right? So we find evidence of stuff like this, right? Based on the various fossil records we have. So then we can talk about the era. As far as the era is concerned, in the Phanerozoic aeon, we have the Paleozoic, Mesozoic, and then the Cenozoic eras. All right, Paleozoic, Mesozoic, and then the Cenozoic. So the dinosaurs, where did the dinosaurs come about? So the dinosaurs came about in the Jurassic period. That is why we have the movie or these films of the Jurassic Park, right? In the Jurassic period of the Mesozoic era in the Phanerozoic Aeon. All right, the dinosaurs appeared in the Jurassic and they died off. The dinosaurs died. They appeared in the Triassic, and by Jurassic, the last dinosaurs died. All right, the last dinosaurs died. And then by the time we got to the Tertiary era, most of the mammals developed and became dominant. By the Quaternary, we had human beings as we know them today. So this is the human lineage. We started with the Australopithecus, and then we know we developed and developed, evolved and evolved, and we continue to evolve. So the current species of Homo sapiens. Homo sapiens. All right. So currently we have Homo sapiens. All right. So this is the whole concept of geologic time, and we are able to tell the number of millions of years ago based on the organisms, the fossil records that were in the various rocks. All right. And then we are also able to tell what is older than what or when the various animals or organisms existed. So life as we know it originated during the Archean, right? Life originated from the Archean, and then living organisms then evolved and then became common or proliferated during the Proterozoic Aeon. So protero is just from the Greek roots meaning earlier or before, and zoon, as we know, means life, right? So however, most of the Proterozoic organisms had no hard parts such as shells or bones. So they were essentially unicellular organisms. And then with time, Proterozoic Aeon ended about 538 million years ago. And then in human beings came much recently as we see it. So astonishingly, just within a period of 5 million years, many new species evolved. And these organisms were biologically more complex, and they had a lot of shells and skeletons compared to the various ancestors in the Proterozoic era or Aeon, or is that not it? All right. So that's exactly where we particularly see. So from Proterozoic, just after Proterozoic, within this time of recent life called the Phanerozoic, we had all these organisms. But before we got to the Phanerozoic, we didn't have a lot of organisms, right? And they were mostly unicellular, bacteria, algae, and all that. Then just within a period of about 5 million years, we had a lot. All right, and a lot within a period of 5 million years. So the most recent 13% of geologic time is what we are calling Phanerozoic. And Phaneros is Greek for evidence. All right, so we have Paleozoic, that is ancient life, Mesozoic, middle life, and then the Cenozoic, which is recent life. So this geologic column or time scale is able to provide us a fair idea of the various aeons, eras, periods, epochs, and then what ages. And then we are able to tell, divide this particular geologic time into smaller units of known relative ages. And we are able to identify or understand what happened in the various periods or epochs or eras or aeons. All right. So the largest of these units, we call that the super aeon. All right. And it's composed of aeons. Is that not it? Then we divide aeons into eras, eras into periods, periods into epochs, and finally we have ages. We could also deal with terminologies like eothem, erathem, system, series, and stages. And these are used to refer to the layers of rocks that correspond to these periods of geologic time in the Earth's history. So that is all I would want us to know. And then we have this international chronostratigraphic chart. All right. And this covers everything as we know it. All right. From the Hadean all the way to the Phanerozoic. All right. So this is where I would like to pause for today.